Welcome to the Pioneer training video for the calculation of takeoff and landing performance data in the British Aerospace 146. This video will step you through some worked examples calculating takeoff and landing performance cards based on the method developed in the Standard Operating Procedures Manual, Issue 4. By way of preparation, we suggest you review the published material so that you're least familiar with the process. While some of the procedure relies on documents you're familiar with, such as runway analysis charts and speed cards, the new engine thrust tables card is a new document that will find its way onto our flight decks, along with a completely revised takeoff and landing data card format that we'll see when the new SOPM goes live. Meanwhile, the process for calculating the takeoff data and the landing data is also comprehensively covered in the SOPM. Your best training experience is if you work alongside these videos, developing your own copy of the solution you see developing on the screen in front of you. To do this, you're going to need one of the new format takeoff and landing data cards, access to the Runway Analysis Chart Manual, or RACM as we'll be calling it from here on in, the new engine thrust table card, a set of 146 speed cards, and also from the front of the RACM, the list of airports and noise abatement profiles. All of this material is accessible electronically inside Comply 365. Before we dive into the example scenario, a quick word of explanation about this diagram you'll find in the SOPM. While it looks complex, this diagram breaks down takeoff performance calculation into its most essential elements on your way to producing a safe, optimized, and ideally flex thrust solution. Like anything colored purple in the SOPM, or in this case, purple edged boxes, if you click on the purple, your PDF reader will jump to that section of the SOPM and explain or provide a detail of what you've clicked on. At that point, your PDF reader will have a back button, which can then be used to take you back to where you last jumped from, which in this example would be this diagram in the SOPM. All right, let's move on to the example scenario. Our second example is a departure from runway 29 centre in Bankstown, where the temperature is 8 degrees, the runway is wet, and it's raining. Pretty much screams engine anti-ice, doesn't it? The QNH is low, which is also not helping, and the takeoff weight is just under 35 tonnes. Also, we're in a 200 series aircraft. Let's go into it, shall we? Step 1 is the flight identifying details and the weather. So first of all, let's head to the top of the card with the airport and the flight number. If we had a BAe, we'd stick that in there too. Moving on, let's put the pertinent weather from the ATIS into the weather box on the card. Based on the ATIS, we'll stick the runway in as 29 centre full length. We can also indicate that the runway is wet, which has been done here by crossing out dry, but of course you can use the method to circle wet if you want, just keep it consistent through the card. And at this point, we need to accept the inevitability of engine anti-ice on. Okay, so with step 1 complete, it's time to move on to step 2. Now we have a load and trim sheet. The load and trim sheet comes with confirmation of the P/B, so we can enter that in the identifying box at the top. Now we can take the takeoff weight from the LTS, round it up to the next 100 kilos, and enter that into the TOW box. We'll also take this opportunity to grab the zero fuel weight from the LTS and record it on the landing card for later, once again rounding up to the next 100 kilos. Finally, the elevator trim can also be entered into the elevator trim box. Note that if we're in a -300, we just enter the final trim setting that we'll be checking with the before takeoff checklist, and we don't enter any indication of flap trim compensation that we would initially set during pre-flight. We'll keep the card simple. With step 2 complete, we're moving on to step 3, the RAC manual. Step 3 is the RAC manual. The first challenge is making sure we have the correct page. We need the correct book for the series of aircraft, remembering we're in a 200 today. We then need to find the airport and the runway, at which point we might need to go back and check there isn't a NOTAM watch chart that we should have gone to instead. But continuing on, the most obvious thing here is the light blue page, because we're operating off a wet runway, also indicated by the wet notation towards the top left-hand corner. Meanwhile, we're in Bankstown, so the runway is shorter, and a wet runway is never good for stopping in an aeroplane without reverse thrust, so we're looking at flap 24 for our takeoff, while wondering in the back of our minds as to whether today is the day we use flap 30. The last factor to consider is whether we can use a straight-out engine departure and make the pilot flying's day, or should we be opting for a special departure procedure in order to optimize performance. In this case, we're going for full-length runway 29 center, no intersections, straight out on a wet chart, and no other aircraft taxiing in our way. Having chosen our RAC manual chart, we'll move on to step 4, looking at the weight adjustments. Step 4 is calculating the performance adjustments we need to make for any tailwind, low QNH, or dispatch with defective lift spoilers. Don't forget that we never use the engine anti-ice adjustment in the RAC manuals, as these are not valid when considering a flex calculation. Instead, we use the 12-degree method, which we'll get into later. In this case, the only adjustment we need to consider is the low QNH. So let's indicate that on the card, in this case by crossing out tailwind and spoiler indications. So, onto the low QNH. With a correction factor of 52 kilos per millibar and 7 millibars to correct for, we end up with a 364 kilo adjustment, which we'll round up to 400. As a weight penalty, we write that as a positive number because we're going to add it to our planned takeoff weight to produce a CTOW, which makes it easier to compare with the RAC manual RTOW limit weights in step 6 and step 8. Let's write 0.4 in the adjustments box. That's it. Remember that if you were really trying to optimize performance, not so much trying to get the best flex today, but trying to get the most payload off the runway in quite limiting conditions, you could use the headwind to account for better performance. We're done with step 4, on to step 5, where we calculate the CTOW using our new adjustment number. Step 5 is the corrected takeoff weight, or CTOW. Once again, straight from the card, it's a simple addition to take the takeoff weight and add the adjustment. 34.7 tonnes and 400 kilos gives us a CTOW of 35.1, which we write on the card. And that's it for step 5. Let's move on to step 6. Okay, step 6 is where we get busy. We are asked to check if the RAC manual RTOW limit weight is greater or equal to the corrected takeoff weight we previously calculated. What we're actually asking is, can we take off under these conditions using full reference thrust? The first thing we need to do is actually determine what is the limiting RTOW from the RAC manual. Remember that in this case, we are engine and ice on, and we are not using the RAC manual adjustment. So we need to use the FCOM 12-degree method. So in this case, we don't go into the chart at the ambient temperature of 8 degrees. Instead, we add 12, and we head in at 20 degrees. From 20 degrees, we head across to the right to our selected runway intersection column and look at the runway limit weight. In this case, it's 39,333 kilos. As always, we need to continue across to the right to the climb limit weight, again at our augmented temperature of 20 degrees. Today, it's 42,184 kilos. As we complete our little table here, we can see that the RAC manual RTOW limit is indeed greater than the corrected takeoff weight by just over 4 tonnes. The upshot of all this is that we can actually take off today if we need to with full reference thrust. On the other hand, If we can't take off today using reference thrust, we need to go back to step 3 and reconsider some of the fundamental conditions. Can we get a longer or different runway, a different flap setting? Do we need to offload? Right, time to move on to step 7 and work out if we can flex today. With a CTOW of just over 35 tonnes and an RTOW limit at full thrust of over 39 tonnes, it's looking good so far. Before we get into the nitty-gritty of flex calculations, it's important to stop and ask yourself if you can flex today. There are a few operational considerations here. Firstly, if we have a wind speed in excess of 25 knots from a direction off the runway greater than 55 degrees, the FCOM says don't flex. If we have reported or otherwise probable wind shear, don't flex, and potentially don't take off. Finally, if we're conducting low visibility operations, once again the FCOM says don't flex. Decided that flex is operationally acceptable, now we need to check the performance. As indicated in the last slide, your potential to flex is in the margin between your CTOW and your most limiting RTOW. In this case, we have 4.2 tonnes of performance to play with, so let's move on and calculate the flex. So having concluded from the previous slide that we are going to flex, now let's see if we can jump straight to the finish line and use max flex. For most takeoffs, there's a flexible thrust range between the lowest flex temperature, based on the ambient temperature and the engine flat rating, and the maximum flex temperature that gives us our lowest N1 flex we're allowed to use, which in this case, with engine and ice on, is 87%. How do we work out that range? The engine thrust table. This table is designed to make it straightforward to calculate your theoretical minimum and maximum flex temperatures based on outside air temperature and your engine and ice status. Today we're looking at the blue card for engine and ice on. Unlike the RAC manual, we go in here at our actual ambient temperature. That's because this table is designed on the assumption that engine and ice is on, so we do not need to make a temperature correction. Now we'll go to the right, in this case to the first valid flex temperature we can actually use, the lowest permitted T-flex. This is the beginning of our range. Here we'll continue all the way to the end to find our theoretical maximum temperature, which in this case is 26 degrees. Once again, it's theoretical because while 26 degrees is a valid flex temperature, we don't yet know that it will generate enough thrust to satisfy the performance requirement. But for now, it gives us our range. To work on the performance part of this problem, we return to the RAC manual. Because we are engine anti-ice on, we need to add 12 degrees to those minimum and maximum flex temperatures when we head into the RAC manual. This is an important point. When we're dealing with the engine thrust table, we use actual temperatures, we get actual temperatures because the card itself is designed around the use or non-use of engine and ice. But when we head into the RAC manual chart, if we're engine and ice on, we have to add 12 degrees. In this case, our flexible range of 16 to 26 degrees from the engine thrust table becomes 28 to 38 for the RAC manual chart. And so using 26 plus 12 equals a 38 degree max flex temperature, let's see if we can use maximum flex and get off our runway. So starting at our 38 degree line, we head across to the right and once again look at the two limiting numbers, the runway RTOW limit and the climb limit. We can see that at 38 degrees of flex, our most limiting weight of 35,356 is greater than our CTOW of 35.1 tonnes. So the answer is yes, we can use maximum flex. If we weren't able to use maximum flex, our process suggests looking at a different flap setting or some other change that would allow us to use maximum flex. We'll have a look at this case in another example. For now, we are going to use max flex for takeoff, so let's finish off step 8. And continuing on with step 8, we've established that we can use the maximum flex temperature from the engine thrust table today. So let's go ahead and record the details of that performance on the card. In this case, we'll round the RTOW limit from the RACM down to 35.3 and write it into the RTOW limit box. And we also want to make a note of the limiting V1 from the RTOW limit performance in case this limits us against the speed card V1 later on. In this case, maximum V1 is 91 knots, not unusually low for a wet V1. We're done with the RAC manual now. Let's move on to step 9. All right, step 9 calculates our TOW limit for the card. That is, with the flex that we've decided to use, in this case max flex, what is the maximum takeoff weight we can lift today? We do this by taking our RTOW limit and subtracting from it the adjustments we calculated in step 4, which was for the low QNH. So continuing through the card, if there was some doubt about the intersection previously, perhaps we were not using full length from choice, then right now we would finally populate that intersection. In this case, we're always going to use as much runway as we can get our hands on, so it stays blank. So we can now take our flex temperature, in this case we're using max flex, and write that in the T-flex box. Note that here we're taking the flex temperature we validated in the RAC manual and subtracting 12 degrees because we're engine anti-ice on, and writing 26 on the card. Why? Because this temperature is going into the TMS, and the TMS knows all about engine anti-ice, or at least it does if we have it switched on and we set it up, and later on when we're taking off. Once again, the only place we do and must add 12 degrees is when we're entering the RAC manual, and then you have to remember to take that 12 degrees off when you're pulling temperatures out of the RAC manual to use in the real world. All of this based on being engine anti-ice on for departure. And since we have ended up within 200 kilos of our performance limit, we are required to do a standing takeoff. So let's cross out the option of a rolling takeoff on the card. And finally, let's write takeoff flap in the card, nice and big. Time to move on to step 10, the thrust settings. For that, we're back to the engine thrust table card. And here we are in step 10 for the thrust settings. We need to calculate our flex thrust N1, our reference thrust N1, and our climb thrust N1. We're back in the engine thrust table once again, and this time the blue card for engine anti-ice on. So starting with N1 ref, we start at the actual ambient temperature of 8 degrees, work our way left to the pressure altitude, which in this case is slightly closer to sea level than it is to 500 feet, and so the N1 ref is 92.3%. And the climb thrust N1 is found in the grey column next to our ambient temperature of 8 degrees. In this case, with engine anti-ice on, it's 87%. And finally, the flex thrust N1 also comes from the engine thrust table. Note that I've just split the table into two sections here just to make it easy to read, but basically we start again at the same ambient temperature of 8 degrees. This time we're heading across to the right to the flex temp that we're going to use, in this case max flex of 26. From there we go down to the N1 flex, 87%, which we know is the minimum we can use for engine anti-ice on. So much for step 10. Let's move on to the V-speeds in step 11. So the V-speeds come mostly from the speed cards with a couple of caveats. First, we'll round up the takeoff weight to 35 tonnes to select the correct card. So from the 35 tonne card, flap 24 takeoff, the VR and the basic V1 is 111 knots. Now we need to correct this for temperature and pressure. So our final toll card VR will be equal to the speed card basic VR with a correction from the VR correction table. In this case, 8 degrees of ambient temperature and sea level comes with a correction of -1 knot. So the VR for the toll car is 110. Next, we occasionally need to consider a V2 correction, but since it's only required in the 200 series for takeoff weights of 28 tonnes or less, it's not applicable today, and the speed card V2 of 118 knots can go straight onto the toll card. Moving on, our V1 must always be the lower of the RTOW RAC manual limit V1, which we made a note of earlier, and the corrected speed card VR. In this case, the lower of the two speeds is the wet 91 knots. Time to fill in the V1 on the toll card. We're almost there. We can grab the VFTO of 169 from the speed card and write it on the toll card. And that's pretty much the end of the speeds for the toll card. And just a reminder that while we don't write the VAR speed on the toll card, we will be bugging it from the speed card onto the ASI where it's always VFTO plus 10 knots. Let's head towards the finish line of step 12, noise abatement. While the source document for noise abatement is our JEP charts, Pioneer published a quick reference noise abatement list at the beginning of the RAC manual. This list conforms to any specific noise abatement departure procedure dictated by the airport authority, as well as Pioneer's SOP preference for NADP 2 when noise abatement is required but no specific procedure is specified. As always, indicate on the card the requirement. That's it for step 12, on to lucky 13. Our final step is to record onto the toll card the engine out procedure and the engine failure flap retraction altitude, or EFFRA. Remember, of course, that if we have DP in the runway intersection name, then there's a special departure procedure to go looking for in the RAC manual. But in this case, it's a straight out departure, which means straight ahead to 20 miles, establish a left-hand 5-mile holding pattern. And finally, our minimum engine failure flap retraction altitude is published in the RACM here as 1070. We'll round this up to 1100 for altimeter bugging purposes and record it on the card. With the card complete, it's time to hand it over to the other pilot for an independent cross-check. While this procedure is covered in the SOPM, the following points are worth noting. Cross-checking is a skill that, first of all, requires the knowledge and understanding of how the card was completed in the first place. You can't cross-check a card if you don't know how to prepare one yourself. Cross-checking requires you to consciously avoid or look for prejudiced information. This includes looking at the ATIS yourself, the load and trim sheet, the RAC manual, the thrust card, and the speed cards. In all cases, finding the correct page yourself rather than accepting a previously selected page by the other pilot. With the toll card complete and cross-checked, before you hand the card back to the other pilot, independently set your speeds. When the card is returned to the other pilot, he or she should also independently set their speeds, at which point the TMS setup, N1 bugs and airspeed bugs cross-check can begin. That's the end of this example. Thanks for playing.